Today we're diving deep into the paper, Hover, Versatile Neural Whole Body Controller for Humanoid Robots. This research tackles a significant challenge in humanoid robotics, creating a controller adaptable to diverse tasks. What are the key limitations of existing humanoid whole body control approaches that Hover aims to address?
Existing approaches often train individual policies for specific command spaces. A policy optimized for navigation, route velocity tracking, won't seamlessly transfer to a task requiring precise manipulation, for example, joint angle tracking. This necessitates repetitive and time-consuming retraining for each task, limiting versatility and scalability. Hover aims to overcome this by unifying multiple control modes within a single policy.
The paper highlights the concept of full-body kinematic motion imitation as a common abstraction. Can you elaborate on why this is a suitable foundation for a multi-mode controller?
Human motion is inherently versatile and efficient. By imitating large-scale human motion data, the controller learns fundamental motor skills, balance, coordination, precise limb control that generalize across various control modes. These shared skills provide a robust foundation, unlike task-specific policies that might overfit to their training environment.
The paper describes Hover as a multi-mode policy distillation framework. Can you explain the distillation process and its role in achieving multi-mode control?
Hover distills a generalist policy from an oracle policy trained on human motion data. The oracle serves as a teacher, demonstrating diverse motions. The student, Hover, learns to mimic these motions under various command masks, which selectively activate different parts of the unified command space: kinematic position, joint angles, route tracking. D-Agger is used for supervised learning, aligning the student's actions with the oracles.
The unified command space is a key aspect of Hover. What criteria guided its design, and how does it achieve generality and atomicity?
The command space needed to be general enough to encompass existing control modes and expressive enough to interface with various real-world control devices, joysticks, VR, etc. Atomicity was crucial to allow arbitrary combinations of control options. It's structured with upper-lower body regions and 3 modes: kinematic position tracking, local joint angle tracking, and route tracking. A masking mechanism allows selective activation of these components.
The paper mentions motion retargeting from human motion capture data. What steps are involved in this process, and why is it crucial for training the oracle policy?
Retargeting involves mapping human motion capture data to the humanoid robot's kinematics. This is a 3-step process. 1, computing humanoid key point positions via forward kinematics. 2, fitting in a simple model to match the humanoid's kinematics. 3, retargeting the amassed dataset by aligning corresponding key points. This ensures the oracle learns feasible and physically realistic motions for the humanoid.
The experimental results show Hover outperforming both specialists, single-mode policies, and a multi-mode RL baseline trained from scratch. What counts for this superior performance?
Hover's advantage stems from the shared motor skills learned through distillation. The oracle policy provides rich motor priors, enabling better generalization across modes. Specialists, trained individually, often overfit to their specific reward structures. The multi-mode RL baseline, lacking the benefit of the oracle's pre-trained skills, struggles to achieve the same level of performance.
The paper demonstrates Hover's effectiveness in both simulation and on a real Unitree H1 robot. What were the key findings from the real-world experiments?
Real-world experiments confirmed Hover's superior performance in tracking various standing motions compared to specialists. Furthermore, it demonstrated seamless transitions between modes during locomotion tasks, even example switching from navigation to manipulation, and robust performance in a teleoperation scenario with Vision Pro, even with occlusions in the reference motion.
How does Hover compare to other approaches aiming for unified or multi-mode humanoid control, such as MHC or Masked Mimic?
MHC, while using retargeted motion, doesn't support arbitrary subsets of modes and is limited in its control options. Masked Mimic, from the computer graphics domain, uses distillation but requires training additional policies and uses simplified humanoid models. Hover distinguishes itself by directly controlling a real-world humanoid with a unified policy and a broader range of control modes.
What are some of the limitations of Hover, and what avenues for future research do you see?
While Hover demonstrates significant progress, future work could focus on developing an automated mode switching module for more autonomous operation. Exploring more sophisticated reward functions and incorporating more complex environmental interactions are also promising directions. Further investigation into the robustness of the distillation process under noisy or unpredictable conditions would also be beneficial.
The paper mentions the use of different reward components, penalty, regularization, task reward, in training the Oracle policy. Can you elaborate on the design choices and their impact on the overall performance?
The reward function is carefully designed to balance several factors. Penalty terms discourage undesirable behaviors like exceeding joint limits or falling. Regularization terms promote smooth and physically realistic motions. Task rewards incentivize accurate tracking of the desired commands. The specific weights for each term are tuned empirically to achieve optimal performance. The balance between these components is crucial for learning robust and efficient movements.
The choice of D-Agger for policy distillation is interesting. What are the advantages of D-Agger compared to other imitation learning methods in this context?
D-Agger's iterative data collection and training process is well suited for this task. It allows the student policy to learn from increasingly diverse and challenging examples provided by the Oracle. Other methods might struggle to handle the complexity of the multi-mode control problem and the high dimensionality of the state and action spaces. D-Agger's ability to iteratively refine the dataset makes it particularly effective for this application.
The paper mentions the use of domain randomization during the training of the Oracle policy. How does this technique contribute to the robustness and SIM to real transfer capabilities of Hover?
Domain randomization introduces variability in the simulation environment, physical parameters, sensor noise, etc. By training the Oracle policy in this randomized environment, it learns to generalize better to the real world, which inevitably differs from the simulation. This helps to mitigate the sim to real gap and improve the robustness of the learned policy.
In summary, Hover presents a significant advancement in humanoid whole body control. Its unified approach, leveraging policy distillation and a comprehensive command space, offers a more versatile and efficient solution compared to existing methods. Thank you for this insightful discussion.